Assalamualaikum and good day everyone. So today is 27th of May 2021, 1 a.m. So we will continue what left of chapter 11, which is latches and flip-flop. Okay, you have learned this in the previous lecture video. Okay, so and also some other demonstration that I do. Okay, so now we just continue, okay, from this chapter. Okay, so now, okay, you may refer to your slide, and also if Thomas and Floyd book if you have, and also please do exercise. It is for your own benefit, okay, for the exam and test, and also past test and past final year. Okay, so if you didn't do any exercise, you will know whether you understand the topic or not. Okay, so now let's we go for the next. We continue from this, which is the T flip-flop. Okay, the T for toggle flip-flop has two input, which is a clock input and a T input. So we have a clock and we have T. Only we have these two inputs. Okay, so when T is 0, okay, when T is 0, clock pulses do not affect the output. Okay, if we set T equals to 0, we will not consider the effect of the clock. Okay, so you see when your T is 0 here, okay, what you have is you hold the values. Okay, Q hold. Okay, when T is 1, when clock pulse arrive, the output toggles, meaning that if the output is 0, it becomes 1, and if it's 1, it becomes 0. So you can see if you set T equals to 1, okay, and when the clock pulse arrive, like this is positive edge trigger, then this output will toggle from the previous inputs. Okay, Q plus will toggle the previous input of Q. Okay, so if this is a positive edge trigger, right? Okay, then if you see from this flip-flop timing diagram, okay, so if you see this is your T, okay, and you start, for example, your T is increased here, okay, then you have positive edge trigger. Okay, however, that time your clock is not yet positive edge trigger, so you won't have anything. So then when you start to have the positive edge trigger, what happened to your Q is that your output will toggle from the previous input. Okay, because you have negative, you have positive edge trigger and T is set to 1. That's why it is toggle from 0 until 1. Then after that, okay, when you have your T is equals to 0, it will hold the value of the previous output as it current output. Okay, so that's why it's hold the value. Okay, it's hold until here. Then when we have a positive edge trigger, however your T is 0, okay, so it still hold. That's why it still hold the value. Okay, so you need to understand the functionality of the circuit, the logic symbol, the characteristic symbol. Only then you can derive the timing diagram. Let's say we ask you in the final about the timing diagram, you must be able to maybe to draw or maybe to explain to us what is actually happening, right? So then when you start having T is 1, then you start having positive edge trigger, then you toggle it. So toggle from 1 until 0. So the same goes. Okay, then we go for the next one is the characteristic equations and excitation table. Okay, so I try to teach from the module as much as possible, because when I use the module, indirectly you guys that doesn't have the module will see the module, right? Okay, you can simply pause the video to read the books. Okay, read the module. The classification of flip-flop specify the flip-flop next state as a function of its current state and input. Okay, so this is what's special with the just like I told you guys, right? The special of the flip-flop and also this chapter. Okay, because we consider the previous output as our input, okay, is current state. Next state as a function of its current state and inputs, okay. Current state can be your current output, okay. The excitation table shows the minimum input necessary to generate a particular next state, okay, minimum, okay, minimum, and this is the excitation table. So please know the differences, okay, excitation table, characteristic table, okay. The excitation table is obtained by rewriting the characteristic table. So this is your characteristic table, and this is your excitation table, okay. So rewrite this characteristic table in order for you to have the excitation table. Instead of the input being present, input being the present state and flip-flop input and the output being the next state, the inputs are now Q. Okay, the inputs are now Q in your excitation table, and Q next and the output are the control bits of the flip-flop. Both the characteristic equation and excitation table can derive from a flip-flop characteristic table. Okay, so your characteristic equation and excitation table can derive from your flip-flop characteristic table. For example, this one. Okay, so we see example of our characteristic table and our excitation table. You see, this is your characteristic table, okay, and this is excitation table. Excitation table, the input is being the present state. This is your input, so it's different, right? Okay, you can see the difference, okay. So then this you have your next state, okay, then you have these characteristic equations, okay. So I think you can spot the difference. Next, D-flop is easiest to analyze. The output after arrival of a clock pulse is the input before the arrival of the clock edge. Figure 11.27 gives the excitation table and characteristic equation for the D flip-flop. Okay, the output after the arrival of a clock pulse is the input before the arrival of the clock edge. Okay, I think this one is straightforward. Okay, D flip-flop toggles its output if T is high when a clock edge arrives. Figure 11.28 gives the excitation table and characteristic equation for the T flip-flop. So T flip-flop toggle is input when your T is high, and when the clock edge arrives, let's say it's a positive edge trigger, okay, so then it's have toggle. For the next state, we toggle from the previous outputs, okay. So this is your characteristic table, and this is your characteristic equation with regards to Q plus with in relation with the Q, okay. And excitation table, like we mentioned before, excitation table it have present state as the input, okay. Then we have this next step, okay. So JK flip-flop shows this figure 11.29 shows the excitation table and characteristic equation for JK flip-flop. Okay, now we have your JK flip-flop. Okay, so I think you guys understand from the previous explanation on the JK flip-flop, right? So I think you can relate here. Q plus equals to JQ plus KQ bar. So if you see this is what it seems to related to which gate. If you see it, okay, I left for you to guess, okay. Then we have present state in the excitation table as your inputs, okay, and your next state, and in the JK flip-flop, so you have this 0, okay. So if you see from here, 0 1 means that it's like a reset, and 1 0 is like a set to 1, okay. This is one which we have the toggle. Now the SR latch is not strictly a flip-flop, but it included here for the sake of completeness. Okay, for the SR latch, SR must not be 1 at the same time. Yes, this one I think you guys already learned from the previous lecture on the your previous reading. If we have both 1, then our both Q and Q bar will be low, right? Which is forbidden. We cannot have Q and Q bar having the same value of 0. Okay, because if Q is 0, Q bar should be 1, something like that, right? So that's why this one is forbidden. So characteristic equation is valid. This equation is valid in the case of SR not equal to 1. Then this excitation table, okay, we can see the present state as the inputs and next states. Okay, you guys can try this at home, okay, to make sure you can try this at home and make sure you get the same answer. Okay, now flip-flop conversions. Okay, we have seen 4 types of latches and flip-flop. In practice, engineers do not need to stock up for all types. So we can use actually JK flip-flop in order for us to obtain different types of other flip-flop. Okay, for SSI level design, this feature to reduce the need to stock up. Of course, if we can use one general flip-flop in order to make another flip-flop, it will be contribute to a great cost reductions. Okay, and we don't need to use multiple chip types. So for example, if we want to implement D flip-flop, we put inverter with our JK flip-flop. Okay, and if we want T flip-flop, we will connect both input on a JK flip-flop. Okay, so here you can see from the JK flip-flop, you can obtain D flip-flop by having inverted here connected to your K. And how about to obtain T flip-flop from JK flip-flop? You just connect both of these to the same inputs. Okay, now in modern digital system design, the flip-flop is more common. A flip-flop can be converted to another type by implementing the characteristic equation. The characteristic equation of the T flip-flop is Q next equals to 2T XOR, I think this one is XOR Q. The T flip-flop can be constructed by feeding T XOR Q into the D input as shown in figure 11.32. You can see it's the XOR. Okay, you just need to connect with a XOR. So you can see this is the equation. This T, I think they show. Okay, they show here. Okay. Okay. So when T is low, input T is equal. I think as you need to make sure you understand how XOR operate, right? Okay. Then we go to the next one. Okay, this one is Q next. Okay. So this one is like XOR. Am I correct? So flip-flop timing, input signal to flip-flop must meet 2 timing parameters before the signal are considered valid. So we have to set 2 input signal. We have that we must be considered so that these signal are valid. So the setup time and hold time. If the setup and hold time parameters are not met, the flip-flop is not guaranteed to recognize the control inputs. Okay, so it's important to meet the condition for this setup and hold times. So here is an example where you build a JK flip-flop, okay, with a D flip-flop. Okay, you want to build a JK flip-flop, you see, from a D flip-flop. Okay, continue. Okay, therefore the signal must maintain the same value before TSU. Okay, what is TSU? TSU is setup time. The time of a control input must be maintained before the clock transition. So we must maintain this control input before we have our clock transition until after TH for proper flip-flop operation. So we must maintain until we have TH. The time a control input must be maintained after the clock transition. This one is before the clock transition. This one is after the clock transition. The third most important flip-flop parameter is the clock to output delay. Okay, which is what is a clock to output delay? Is the time a clock edge is given to change in the outputs. Okay. Changes in the data input have no effect unless a clock pulse arrive. Okay, like just like what you learn, right? Negative edge trigger, positive edge trigger. Okay, so it's changes in data. We will not have any changes in our data input if we don't have any arrival of clock pulse. Okay, when clock edge arrive, then only flip-flop can change its output. We only change output if we have change in our flip-flop. Therefore, propagation delay is not measured from changes at the data inputs, but the clock inputs. Okay. Propagation delay can be different for low to high and high to low transition. Okay, so this is the summarize. Okay, then we go to the last. Okay, we're about to finish this chapter. So we go to this flip-flop integrated circuit. So flip-flop IC. So we have example flip-flop IC 74 times 74, which hold 2D flip-flop. Okay, then we have two extra inputs. This one PR is actually preset, and this one is CLR is represent the clear buttons. So the input PR put Q into a logic high asynchronous. Okay, asynchronous. Okay, means is not synchronous with the clock pulse. Okay, the input clear puts Q into logic low. So you can see the difference, right? Okay, PR put Q into logic high. Okay. Okay, and clear put the Q into logic low. Okay, since the device is a positive edge trigger, the input changes the Q output. The input changes the Q output on the rising edge of the clock. Yes, because it is a positive edge trigger. So if you have the clock, so we change when it's happen from low to high, right? Not from high to low. Okay. Now, so-called the 70, okay, and then okay, they shown these types of 74 times shown in 11.35. Okay, you can see 11.35. So where we have these additional pins, which is preset and clear. Okay, if we have the clock is rising edge here, okay, and if you see preset is 1 and preset is 1, you can see there is a clear. Okay, do you see the combination of input first? You see preset, clear, and you have your D and you have your clock. Okay, so preset puts Q into a logic high. Okay, asynchronous without waiting for a clock high. Okay, so we have, let me see, okay, which hold 2D flip-flop. It has two extra. Okay, okay, so you see this one is the positive edge. Okay, this one is the positive edge. So I think this is quite understandable. We see this one is we don't care about the conditions of this D, okay, because when we have clock as 0 to 1, okay, you can see it is actually what they do is hold the values. Okay, so and then similarly, okay, what else that we can see from this graph? So this one, regardless of your clock, okay, regardless of your clock conditions, okay, then you have your preset and set. Okay, so if you have 0 here, okay, then you will have your preset put Q into high. Okay, and then when without having to see the clock, okay, without asynchronous, okay, asynchronous, so we have preset is 1. Sorry, why my monitor is closed, because I want to see the slides. Okay, so you see first here, you can see this one is activated by low, right, because this is inverted. So that's why this one 0. So how about if this 0, then it will put the Q into logic low. Okay, so you can see it's an active low, right? Okay, and then what else we can see from this graph? Okay, then we have this one 0 to 0. This one is not applicable. Okay, okay, I think what else that we can see from here? Okay, this okay, try to study from this. Okay, and this one is actually your D flip-flop, okay, your actual D flip-flop in the IC form. Okay, okay, the next is what, 11.36. okay, so called the 77 times 77 chip is shown in figure 11.36, hold 2 JK flip-flop. Okay, we have 2 JK flip-flop, the main point here. Okay, the chip has PR and clear just like your 74. However, it is negative edge trigger. How we know it is negative edge trigger? Because we have this. Okay, so similarly, okay, but this one is JK flip-flop. Okay, this one is D flip-flop. Okay, so when your JK flip-flop, you have both inputs. You have 2 inputs here. Then you have another preset and you have clear buttons, and this is negative edge trigger. We need to see what happened during negative edge trigger. Okay, and this is your condition whether your clock is 0 to 1. It will hold the previous outputs, and don't care condition of your clock. Okay, and don't care when this one is happen, you don't care about whatever happened, whatever input you have at your JK. Then you straight to see here preset 0 and 1. So what happened? It will set to 1, and you have preset and clear 1 and 0. So you see clear, it will set to 0. Okay, and this one is not applicable. Okay, and this one is negative edge trigger. Only then we start to see the function of the JK, right? You can see this JK 0, 0. What is this? 0, 1. It's like reset. This one is like set. Okay, this one is a toggle. Okay, next we go to this clock integrated circuits. Okay, a clock is simply a square wave alternate high and low state. Each alternate high low forms a clock cycle with specific frequency and duty cycle. I think you guys know what is frequency, what is duty cycle already, right? This one is F equals to 1 over T. This one is what? The active state over the overall state times. Okay, the duty cycle is the fraction of clock period in which the clock is high. I think you know already. The 555 timer, this figure 11.37, is versatile integrated circuits. They can be used to build lots of different circuits, including a clock circuit. It can be used effectively without understanding the function of each pin in detail. Okay, now the 555 can source or sink 200 milliampere of output current and is capable of driving a wide range of devices. Okay, the 555 timer becomes a clock when configured in a stable multi-vibrator mode, as shown in your figure 11.38. The timing during which the output is either high or low is determined externally by the externally connected 2 resistor. We did this one. Okay, for you to determine whether this output is either high or low. Okay, now okay, R1 and R2 and also a capacitors. Okay, the frequency of pulses, okay, pulses is determined by F1 over T. So you can see this equation. Okay, I think this equation is not really difficult to memorize. I hope you guys are able to memorize it. Okay, the duty cycle is determined by this. Okay, R1 plus R2 by this formula, and you have this time high and this for your time to be low. Okay, the timing diagram in which the is T high or T low, right? Okay, now example, find the resistor and capacitor value for 1 GHz clock using the 555. So you see a range of value can be used, but waveform if your duty cycle very close to 50% is desirable. Okay, we can use C equals to 10 microfarad, 1 kilo ohm, and R2 equals to 68 kilo ohm. This will produce a clock with frequency 1.053 Hz. Okay, with a duty cycle of 50.36. Okay, so you can suggest the value of R1, R2, and your C. Okay, and of course you need to relate with your 1 Hz. 1 hertz, you can simply actually put here 1 hertz. Okay, in order to have three, I think you guys know also from additional mathematics or mathematics, in order to solve for 3 unknowns, you need to have 3 equations. Am I correct? Okay, so here we have 1, 2, 3, 4. We have 4 equation which relates to your R1, R2, or C, and duty cycle and frequency. So in case this one is actually more than enough to help you to solve this question. Okay, specifically it's asking for resistor and capacitors. Okay, with that we finish on this lecture. So I hope that you guys can try. Okay, I won't ask you, you will submit, but I won't like forcing you, please, you guys submit, I will cut your mark if you don't submit. No, I will treat all of you as adults. I think you are adults already. When you are entering university, you are adults, so you are expected to do independent study. And of course, I'm here to guide you if you have any problem. But I won't like, I will cut you marks if you don't submit. Okay, if you submit, you will gain the benefit. Okay, you will learn something. Okay, so I won't lose anything, right, if you don't submit or submit. Okay, or I won't gain anything. Okay, so you guys can start doing I think last time you guys try until 11.4. Okay, this one we have discussed in the class. Okay, I remember we discussed in class during the synchronous class, and this one we discussed in the class, but not everyone having the not sure about their answer, right? And I also honestly I don't have the schematic answer, so I need to see your proper answer question in order to see that you are actually answering it correctly. So I think now we left with 11. The one that we didn't touch at all, 11.5, 11.6, 11.7. So you may guys try to solve this. Okay, in the group, of course. And with that we finish about this latches and flip-flop. So you see this one is kind of funny, but it's look like true as well. If you see, this is Android, N, you see it's N shape. Okay, and this Odroid is look like an OR gate. And non-Nandroid, you have this one, you just put another inverter like a cape, then become Nandroid. This one is Nodroid. Okay, then you OR gate, then you put just a so it's look like it's finally is they are represent the gates. Okay, so with that we finish, and see you in the next lecture. Assalamualaikum warahmatullahi wabarakatuh, and good day everyone. Okay, take care.